Oh, there we go.
Yeah.
Okay, so the goal of this presentation is to provide you with a sort of accessible summary of how we do multiphysics analysis of nuclear events at FY, essentially what often is called fusion analysis, and sort of motivate national data centers to do this kind of analysis. And we'll use the excellent MPE exercise from last year as an example, where I will apply the technique that we use to this exercise simply. Okay, so let's start. So this is, of course, you all know this, I'm sure, but just to take you through all the main signal sources that we're dealing with. Starting from the top right to your top right and going clockwise, we have infrasound, which are, of course, acoustic pressure waves traveling at slow speed through the atmosphere. And understanding that requires an understanding of acoustics. It requires typically an understanding of seismology. There's a big overlap there. And also meteorology. Then we have radionuclides, which are particles in various forms, from the smallest atoms and nuclei via molecules up to amorphous sort of compounds in particulates. And understanding all these different things, this type of signal carriers, you need to know about nuclear physics, of course, radiation physics, but also chemistry and meteorology and a lot of different things. Next, hydroacoustics, which are, again, pressure waves traveling at slightly faster speeds in the oceans. Then, of course, you need to know about oceanography. That's a hard word. And fluid dynamics and seismology and things like that. Then we have seismology, which are, again, pressure waves, but also, since it's solid materials, we have shearing waves, slightly faster traveling speeds, which, of course, then requires you to have seismologists to understand this, but maybe also geophysicists. And then, which is not necessarily treaty, or it isn't treaty relevant, but I still want to include electromagnetic radiation in this, the initial light flash, thermal radiation, and then the subsequent electromagnetic pulse that is generated in the atmosphere from rapid ionization of the atmosphere, really, the atoms. I still want to include that here. So, in order to do your best analysis of a given nuclear event, you need to include all these different technologies to your best ability in order to work out the fundamental information about time and place, the depth or height if it was an atmospheric event, and you need to be able to reliably answer the question whether or not it was a nuclear explosion that has occurred. Now this is sort of from an NDC perspective here. And then you would like to say something perhaps about the source term, the yield of the event, if it was an explosion, and perhaps also you want to say something about what type of materials that have been used in the weapon, let's say. And in the end, of course, you want to work out a full, complete scenario timeline that you can report to whatever reporting paths, or whoever wants the information from you, depending on how your institute is set up. But all of this is extremely challenging, so I want to bring forth a few different aspects of why it's challenging here. And one thing that I've been thinking a lot about starting at FY just a few years ago is the communication between all these different disciplines that we just talked about. It's quite tricky for someone working with radionuclides to understand what is going on in seismology and the other direction, of course. So this is important to think about, and you need to be extremely humble. And I like that aspect, but it's a challenge. And of course, since we do event analysis, you need to be careful about the completeness of the event scenario space, given all these different signal domains that we are working in. And then we have heard a lot about the confidence of your analysis here at SNT, and that's always a challenge. But from this aspect, it's really the total confidence that we need to try to work out. It's not necessarily only the ATM uncertainty or the accuracy in your seismic location, say. Let's go back 12 years to SNT 2013, where we presented something along these lines. Anders talked about more the automated data fusion process at that time, but it's still relevant also to a manual fusion process, I think. And the key word here is well-defined. So we'll come back to that at the end. If you have a but what we talked about here is the need to sort of get rid of decision bias, right? And then and that requires you to have sort of a predefined set of criteria that you follow. So that's one of the key things that I want to talk about in this talk. And the rest of the things here, the first 4 bullet points, are really just build a scientifically sound method for fusion analysis. Just skipping ahead a bit here. And the last 4 is, if you have such a well-defined process, there is a possibility to do things like network studies, or you can tune your alarm rates, but you can also discuss with other institutes if you have a defined process. And you can, of course, also write your code. Okay, so let's take an underground nuclear test, and staying with just xenon and seismicity. So then the fundamental criteria that we work with here is starting from the seismic event. It's important that it's not screened out. We think that it is an explosion. The depth is relatively shallow, and things like that. Next, from a xenon perspective, we want to detect one of these important xenon isotopes that are tracers of nuclear events in one or several associated samples. We want to make sure that the background sources are not dominating. And we want to make sure also that the observed isotopic ratios are in the nuclear test domain. And then the times should agree from the seismic and the xenon analysis, and the positions should agree. And then also, if you're able to determine a seismic yield, you want that to fit with the xenon source term. And the idea here is, of course, to have a consistent and coherent picture, and it's important also to not miss any events, right? You want to have a low false negative rate. So if you then translate that to a more general set of criteria, the SHI signals, and so this is now the list that we're going to work with, the criteria, and we want to say yes or no to these questions. So the SHI signals, are they or are they not from an explosion? Are the SHI and RN signals from a background source or not? Are the RN isotopic ratios in the test domain? And then the timings, as we talked about, the locations, and then the source terms. So the yield and the release activity. And then combining all that, you want to answer the final question, is this an anomaly, and what do we do with this? And in the treaty sort of domain, we want to maybe recommend an OSI and things like that, right? So let's now, in the end of this talk, apply this to the 2024 MPE. You heard a lot about this, I'm sure, during this conference and previous meetings, but just to briefly introduce it to you. So there was a fictive state called Atlantis out to the west of the British Islands that called for help to the other national data centers around the world. They provided us with national seismic data, national infrasound data. They pointed to, and they provided one xenon mobile station down at Madeira. And then they pointed to 2 IMS radionuclide detections and 1 hydroacoustic detection. So it's included essentially all technologies. I have to go through this quite quickly here, but this is just a set of data and the timeline. So at the 14th of January, we got waveform data. 2 weeks later, we had information from DEX and SEX in Germany and Sweden on xenon. And then roughly 1.5 months later, we had observations of xenon at this mobile Madeira station provided by Atlantis. Okay. There are a lot of details to this, and so this data was not necessarily given to us directly. We had to work with it to obtain it in this form. The SHI analysis pointed to some kind of shallow event at the Azores, or the Bezores Islands, as it was called here. And And the radionuclide and ATM analysis to your right showed that, so the left plot there shows different containment times for an underground explosion, and we could show that with a long containment time, roughly 1.5 to 2 months, we could fit the Madeira observations of the Xenon 131M and the Xenon 133, but the IMS detections did not fit with this at all, so they were ruled out. I'll skip the right plot. So the suggested scenario here is that the waveform analysis hinted on some kind of underground activity going on, some kind of underground event. The IMS detections of Xenon was unrelated, but the Madeira station was perhaps, or was related. We could map those, or match those. Just the same thing, but on a map. So something happened on the Bezorus. 1.5 months later, they perhaps opened the cavity, and Xenon was released into the atmosphere and observed on this mobile station down in the middle there on Madeira. Okay, so let's just go back to the criteria and apply these different observations to this list. So we couldn't really say if the from the waveform analysis, we couldn't say if it was from an explosion or not. And the same with the waveform, we couldn't say if it was from background or not. So that's why there's a question mark on the left there, on the second row. Because there are also a lot of earthquakes in this region, and yeah. But the radionuclides, we were pretty sure that this was a real detection, pointing to a nuclear event. The test domain is okay. The timings we could fit, the locations we could fit, but we couldn't fit the release activity with the seismic yield simply because we weren't provided with response functions, calibrated seismic data, so we couldn't reliably produce a magnitude simply. But the combined signal was an anomaly. And then the different NDCs in this sort of role-playing game acted differently upon this information depending on how your NDC is working. So finally, some conclusions. So the idea here was to present you with an approachable and accessible set of criteria, a well-defined approach to fusion analysis with the hope of inspiring more national data centers to do this for maybe the upcoming national preparedness exercise. And the key thing here is to have a predefined set of criteria to avoid bias that you work with, so you don't come up with them as you go, that you have this list. And of course, in this list, there's a lot of details in this and numbers that I don't put down because that will be different for each NDC, right? It's important to have an independent analysis from raw data if you can, but if you cannot, then we have the secure web portal with an IDC's products that we can work with. Scientific communication is a challenge. MPs are great. Sample association in RN is a challenge. And then I want to point to that we are in the progress of developing automatic fusion tools at FY. And me and my colleague will write up a full report. We are in the process of writing up a full report on this MP with these criteria as a basis. And here at the end, I just want to point you to some other FY-related contributions here at S&T. So thank you.
Thank you very much, John. We have a few minutes for some questions. So if nobody's asking, maybe I will ask a question. As part of the fusion analysis that you mentioned, would you consider using a weighting factor for each one of the measurements in order to those measurements that you already fulfill the criteria, and if that will be of benefit?
Yes, that's a very good question, and of course that would be very good. I guess you would have to relate it to how confident you are in each of these different results, of course. This is more maybe for an automatic fusion tool then. So maybe Anders has some more ideas about that I've just been thinking of. But yeah, of course, that would be fantastic in an automatic fashion, but also in a manual. Yeah. Sorry, I can't provide more details on that.
Thank you very much. Any other question? Thank you, John.
Yeah, thank you.
Thank you, John.